In this video, we're going to look at proofs related to eigenvalues. Some very basic, we'll look at some very basic eigenvalue proofs. So let's consider this theorem. Suppose A is an n by n matrix. And lambda is an eigenvalue of A. Then lambda squared is an eigenvalue of A squared. And let's go ahead and prove this. Again, let lambda be an eigenvalue of A. And again, sometimes how people will say this is we'll say that lambda is an eigenvalue. A lot of times they'll represent the spectrum or the set of eigenvalues by sigma A. So they'll say that lambda is an eigenvalue of A, or they'll say lambda is in sigma A. So you might see this a lot. So in any case, either notation you use, so that means that AX equal lambda X for some vector X. So we know because it's an eigenvalue, we have that this is true. Now let's multiply on the left by A. And now, of course, lambda is just a constant. So we can remember when you're multiplying a matrix by a constant or a scalar, you can multiply on either side. These can commute. And in case, so on the left-hand side, if we multiply those two out, we have A squared. If these commute, we can say that this is going to be lambda A X like this, huh? And so let's go to the next step. A squared lambda X. But right over here, what can we substitute for AX? If we look up here, we can substitute lambda X for AX. So we're putting this into here. Be lambda X squared, or lambda like that. Then finally, the last step, lambda squared X like that. So obviously this is the form that we have. Then, if you have, by definition, this is the form of a eigenvalue, an eigenvector. If you have a matrix here, in this case, it'll be produced by this square, and whatever this constant here over here is, that's going to be the eigenvalue, as long as these are the same vectors. therefore, I'll put the 3 dots, meaning therefore, lambda squared is an eigenvalue of a squared. Or if you want to use this notation, lambda squared's in the spectrum. Sometimes they call it a squared, or is in the set of eigenvalues of a squared. Now, of course, you could extend this and make this, you can show that this is true for any power of a. So if you have, say, a higher power of a to the n, and so you can call this, another theorem or corollary. And we're assuming the same condition here. If lambda is an eigenvalue of a, then lambda to the n is an eigenvalue of, and maybe I should say AK. Let me just call this AK to distinguish it from A being an n by n matrix, because K can really be any integer. So lambda K is an eigenvalue of AK, where K is any positive integer. And you could prove that in exactly the same way. You go through the same steps. You just have to do it, like, say, for cubed, you'd have to do it one more time. You could multiply this 3 times. It kind of goes through the process, be a little bit longer. And then you could prove it in general terms, where K is any positive integer. Let's do another theorem. Suppose A and B are n by n matrices. Again, so we're assuming they're n by n, they're the same size. Obviously, if they're both n by n, whatever n is, they're both the same size. And suppose lambda, once again, I'm going to use this notation to say it's in the set of eigenvalues of AB. Then lambda is in the set of eigenvalues of BA. In other words, if lambda is an eigenvalue of AB, it's also an eigenvalue of BA. That's kind of interesting because, in general, two matrices don't commute. In general, AB is not equal to BA. In some rare cases, AB is equal to BA. But in general, it's not true. But on the other hand, if A and B are both square matrices of the same size, and lambda is an eigenvalue of AB, it's also going to be an eigenvalue of BA. And once again, we can prove this. Let lambda be an eigenvalue of AB. then of course what that means is ABX equal lambda x for some eigenvector x like this. So now let's multiply on the left-hand side by b. So we'll multiply this by b on the left. And just like before, of course, a matrix will commute with any scalar. This. And now if we just associate these a little bit differently. So if we just, no, I'm not even going to multiply it by anything or change anything, just put some parentheses here just to emphasize bx like that. So notice that lambda is an eigenvalue of BA because you have BA times this vector equal lambda times that same vector. Therefore, okay. Notice the only difference is, lambda was an eigenvalue of AB. It's also an eigenvalue of BA, but it has a different eigenvector. Over here, the eigenvector of AB was a vector we called X. You could have called it whatever you wanted to. But whatever vector you have here, the eigenvector for BA will be BX. Recall a projection, and let me give you a definition. Matrix A is a projection if A squared is equal to A. So now let's look at a theorem regarding the eigenvalues. Okay, suppose that A is an n by n matrix and A is a projection. That is A squared is equal to A. Then the only eigenvalues of A are 0 and or 1. So let's go through this proof. Let lambda be an eigenvalue of A. Once again, I'm going to write it this way just to save a few steps here. Let lambda be an eigenvalue of A. Then, of course, what does that mean? That means that AX equal lambda X for some eigenvector X. So now we'll multiply on the left by A. Like this, and once again, we can commute any matrix with any scalar. So we can write this way, like this. And now, of course, from we did previously, AX is equal to lambda X. So on the right-hand side, we can replace that. So all I did was just put this into here, then down into here. And on the left-hand side again, this, and then this. Now, and then right here, since A squared is equal to A, we can replace A squared with A. We put a note here, since A squared is equal to A, we're allowed to do that. Now, finally, notice what we have here. We have A of X equal lambda X. And we have A of X equal lambda squared of X. So this line and this line imply that since AX is equal to both of these, then therefore lambda squared has to be equal to lambda. And so what are the solutions to this? Let's rearrange this a little bit. This is going to be, if we move this to the left-hand side, lambda squared minus lambda 0, lambda minus 1 is 0. And lo and behold, what we get is lambda is equal to 0, or lambda is equal to 1. So for projection, the only possible eigenvalues can be lambda equals 0 and or lambda equal 1. So we're going to look at something else. And one thing I want to remind you of is the nilpotent matrix. Is a matrix such that a k is equal to 0 for some integer k. So nilpotent matrix is a matrix that if you take it to a certain power of an integer, you get 0. In other words, you get the 0 matrix. So I want to emphasize that that's the 0 matrix. Obviously, again, it could be any value of k, but if there's any value of k, if k is 2, in other words, if you square it and you get 0, cube it gets 0, the fourth gets 0, any of those, that's a nilpotent matrix. And now, so let's look at a theorem related to that. Suppose A is an n by n nilpotent matrix then all the eigenvalues of A are 0. So all the eigenvalues are 0 if it's nilpotent. So let's take a look at this. Let lambda be an eigenvalue of A, then AX equal lambda x for some eigenvector x. And now from before, recall from the previous theorem we did earlier in the video, we said if lambda is an eigenvalue of A, then now we proved the case for A squared, but as I mentioned, you can extend it to any power of A. Lambda to the K is an eigenvalue of AK for any integer. So that means, therefore, we're going to have AK. And also, as you recall, we also, when we did it for A squared, we end up with the same eigenvector. And same thing here, when you take it to any power, you'll get this here. So therefore, you have this now, and then that's going to be for any k. Now, if we pick the k that makes this 0, then this is going to be 0 over here. Like this. Therefore, of course, that's going to be just 0. Therefore, lambda kx is 0. But remember, eigenvectors are never 0. And this should actually probably be a vector here. Eigenvectors are never 0. Therefore, if you have this to be 0, that implies this has to be 0. So the eigenvalues of a nilpotent matrix are always 0. All of them are 0. So again, recall a similar matrices A and B are similar. And a lot of times we'll write that as A, B like this if they are similar. If there exists an invertible matrix P such that P inverse A P equal B. And as we said that previously, you remember this could be P and this could be called, you can call this P and this P inverse. Or you could write the other way, you could have A equal P B inverse or A equal P inverse B P. Any of those, but just as long as they have this relationship. So now we're going to look at the eigenvalues. And again, we'll look at the theorem. Suppose A and B are similar. And by n matrices, then A and B have the same eigenvalues. There are actually a couple of different ways to prove this. Let me call this. I don't know if I'll have time to do the second proof. Let me just call this proof 1 for now. So let lambda be an eigenvalue of A. Then, of course, what does that mean? As usual, a x equals lambda x for some eigenvector x. So now let's go through steps. Now, again, A is the same as IA. I is just the identity matrix. And now since A is similar to B, we've identified, we know that there's going to be a matrix P that has this relationship. So let's use that P right here. And we call this P inverse AX equals lambda x like this. And let's associate these. Let me just, oh, sorry about that. P inverse A X lambda x like this. And now, so first of all, notice that lambda is an eigenvalue of this. The lambda is an eigenvalue of this. Now, remember from the previous theorem, we said if lambda is an eigenvalue of, say, AB, it's an eigenvalue of BA. So therefore, in this case, we can say if lambda is an eigenvalue of this matrix times this matrix, then lambda is an eigenvalue of P inverse AP, like that. And of course, since that's equal to B, therefore, we can finally say lambda is an eigenvalue of this matrix, which is equal to B, since this right here is equal to B. Now, another way to show this, to prove this theorem, let me call this proof 2, is to show that A and B have the same characteristic polynomial. Remember, the determinant of that A minus lambda I is called the characteristic polynomial. Remember that polynomial that you get when you try to solve for the eigenvalues, you get that polynomial in terms of lambda. Again, sometimes people write that polynomial in terms of x. So if you can show that that characteristic polynomial is the same for two different matrices, then the eigenvalues have to be the same. So we'll show that's what we're going to show in this part here. So once again, we know that B equals P inverse AP. Then again, if we consider the characters polynomial, like I say, I'll put in x instead of lambda. So again, of course, that's x. This is just a variable. It's not a scale. Excuse me, not a vector here. So the term of A, therefore, since this is true, we know that this is equal to determinant of this. Like this. Sorry about that. It's kind of messy. So this is the determinant. There should not have been a parenthesis here. So I'm just replacing this B with this. And so let me keep the left-hand side the same all the time. I'm just going to put continuation marks here. I'm just going to keep the left-hand side the same. And over here, determinant. And I'm going to factor out, let's see. Let's factor out a P from both sides here. It's going to be a P inverse. So I take the P inverse out of here. And remember over here, this can be written as IX. Remember, this is just a variable and sort of a scalar variable. So this is just can be written as IX. And so we could take a P inverse out of the I, and we'll be left with minus PX like this. Or if you want to, I'm probably putting a lot more steps than we need. I could have left that as XP, and then we'll take P out. And so we'll be back to I here. And remember from the property of the determinants, if you have like, say, remember the determinant of A times B is equal to the determinant of A times determinant of B. Same thing here, we have three matrices. And so we can break this up to be determinant P inverse, determinant A minus XI or IX, and determinant of P, like this. And of course, now these are just numbers, and we can always commute these. So we could write this as determinant of A minus XI, determinant P inverse, determinant of P, like this. Now, of course, the determinant of P inverse is going to be 1 over the determinant of P. So this is just going to be 1 right here. And so what do we have? We have determinant of B minus XI is equal to determinant of A minus XI. Therefore, A and B have same characteristic polynomial. Therefore, A and B have the same eigenvalues. So that gives you two different ways of proving that similar matrices have the same eigenvalues. Next, we want to consider the transpose of a matrix. And so, and remember, the transpose when you interchange rows and columns. And so we'll have to recall a few things about transpose. Recall that if you have like A plus B transpose, that's going to be equal to A transpose plus B transpose. That's an unusual property of the transpose. Very few other properties of this type have this relationship. You know, like for example, if you have A plus B inverse, that's certainly not equal to A inverse plus B inverse, but this is true. And now one usual property that's similar to inverse is if you have AB transpose is equal to B transpose A transpose. That's certainly true. And also the determinant of A is going to be equal to the determinant of A transpose. So now we have a theorem. Suppose A is an n by n matrix. Then A and A transpose have the same eigenvalues. And proof, let lambda or let me this time I think I'm gonna go ahead and go with the yeah, I'm sorry. Let's go with this. Let lambda be an eigenvalue of A. And of course, what does that mean? That means if you put the eigenvalue into the characteristic polynomial, you'll get 0. Some sort of more or less when we work on the characteristic polynomial. But we know, of course, that the determinant of A is equal to the determinant of its transpose. So therefore, in this case, the determinant of A minus lambda I is going to be equal to the determinant of this right here. So in other words, we have that's going to be equal to A minus lambda I transpose. And then using this property up here, we can then say the determinant of A transpose minus lambda transpose, like this. Now, of course, lambda, and now if we go through the process, let me go through it. It's a little bit unnecessary because we have a scalar. So you basically would have something like this. You're going to have I transpose lambda transpose. But of course, lambda is just a scalar. So when you take a transpose, you just get lambda back. And here, of course, I is the identity. We take transpose of identity. Remember, identity has all ones on the diagonal, so you take the transpose, you still get the identity back again. So you end up with I lambda, like I said, like this. And then of course you can commute these. Therefore, and now see what this string of equality gives us. We have that this is equal to 0. Therefore, determinant of A transpose minus lambda I is 0. Therefore, lambda is an eigenvalue of A transpose. So we start out that lambda was an eigenvalue of A and showed that it was eigenvalue of A transpose.